everyone feeling today?
Totally awesome, sir.
All right, today's lesson is about the electric field strength inside a conductor. The electric field strength inside a conductor, a piece of metal. So I'm going to start off by posing a question to you guys. I'm going to make a comparison between a tank over here, some sort of tank, and in this tank there's an ideal gas. And the ideal gas molecules are floating around, bouncing off of each other, elastic collisions, and basically they evenly spread out throughout the whole area inside the tank. Yes, they're all moving, they're all going to keep banging into each other, but you get a nice spread of the gas molecules. Well, on the right hand side, I want you to imagine a solid sphere of metal, a conductor. Remember, a conductor is where electrons can easily jump from atom to atom, so they can easily flow throughout. And this piece of metal on the right has extra electrons on it. The question is, would these extra electrons spread out the same way uniformly throughout this sphere over here as the gas molecules did on the left? Would the electrons spread out throughout the metal sphere the same way as the gas molecules do throughout? We know that electrons are negative, and if there's extra negative charges next to each other, we know that like charges are going to repel each other, so they're going to be get away from me, side-kicking each other and stuff. The electrons are going to try to get away from each other, yes? So will they spread out to get away from each other and basically have the same overall look as the gas molecules on the left? You might think yes, but the answer is no. Let me show you what happens. With the metal sphere, if you put on extra electrons, let's say for some way I could place them all like this. And don't copy this down yet. But let's say I could place them all like this, yes? Well, let's zone in on this one electron right here. That one electron, it's going to want to get as far away from all the other electrons as possible. So guess where that electron there, that green sucker, guess where that green electron would go, Brianna and Dorothy? Where would that electron go if it wants to get as far away as possible from the other electrons? To the edge. Yes? It would be like, yeah. It would actually go all the way out here and hang out on the outermost surface. So it would no longer be here. And then this next electron right here, where would it want to go?
To the edge.
To the edge. To get as far away as possible. And if we played this game over and over again, basically all of the electrons end up going to the outermost skin of the sphere. And they would do this immediately. It would be like whoosh! And the next thing you know, you would have this scene right here. You see, the thing is, this electron doesn't just want to get away from its closest neighbor, it wants to get away from all of the other charges. So all of the excess charge would go to the outermost surface. Sometimes this is referred to as like a skin effect. Now, we know that positive charges in a solid metal are the protons that are locked up in the nucleus, and they're not free to jump from atom to atom because they're locked up in the nucleus. However, when we map the invisible electric force field, we pretend to place a tiny imaginary free to move positive charge in the space. So let's pretend, ladies and gentlemen, to put a tiny imaginary positive charge that's free to move inside the space there. Well, how would it respond to this electron right here? How would the tiny free to move positive charge respond to this guy, Paulie?
It would attract to it.
It would attract to it. It would want to go that way, yes? But it would also want to go to the next guy. It would also want to go towards the next guy. It would also want to go towards the next guy, 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 towards that guy. It would be attracted towards all those guys, yes? And in the end, guess what happens to all of those attractions? Read? They cancel each other out. So guess what the overall electric field strength turns out to be inside the conductor? 0. So all of these little forces acting on the tiny imaginary free to move positive charge cancel each other out. And since electric field strength equals the force per charge, if the overall force on that sucker equals 0, then the overall electric field strength is 0. So inside the metal sphere, the overall electric field strength is 0. And it's not just that way for the center point. It's that way in the whole space inside the metal structure. The electric field strength is 0. The electrons repel each other, go to the outermost skin, spread out away from each other in such a way that the electric field strength everywhere inside the metal is 0. So that's a fact you need to know. Now, it doesn't have to be a spherical shape either. It could be like a box. If you had a box like this and you added extra electrons, the extra electrons would spread out as far as possible from each other in such a way that the overall electric field strength everywhere inside would be 0 newtons per coulomb. But here's the difference. If it was a box, the electrons wouldn't be equally spread amongst the whole surface. They would be like a little bit more concentrated, like over here at the corners. how they would position themselves in such a way to get as far apart from as many of the other electrons as possible. Now it turns out that there's a very common application of this. You probably heard that during a lightning storm, one of the safest places to be is inside of a car. Now, unfortunately, many people, including my mom, because I can remember her telling me this as a child, they think that you're safe because of the rubber tires. It doesn't have anything to do with the rubber tires. It has to do with the fact that you're sitting inside of a metal box. So, if you had a car, well, the person can't see over the steering wheel, but nonetheless. Okay. Nonetheless, you're inside the car. If lightning strikes, a burst of extra electrons is thrusted upon the car. So extra electrons come crashing down and hit the car. But when they hit that metal conductor, how do electrons feel about other electrons? They don't like each other, yes? So as soon as they hit that conductor, they want to get as far apart as possible from the other electrons. So as soon as they hit the car, they take the outermost skin down the edges of the car, and the rubber tires, even though rubber is an insulator and usually doesn't allow electrons to jump from atom to atom to get through, the burst of electricity is so strong that those extra electrons, they go right through the rubber tires and into the ground. You're safe inside the car because of the skin effect and the fact that the electrons take the outermost surface down into the ground. And everywhere inside the car, the strength of the electric field is zero. No force would act on you. Even if you took the rubber tires off and the car was sitting on its metal hubs, the inside part of the tire, yes, you would be 100% safe in the car. Now remember, as a young teacher, I told my students for a couple years, I said, I wouldn't want to, put your hand up here and touch the top of the car with your feet on the bottom of the car like that. Because I thought, well, maybe that's like a conducting path, because human beings generally do conduct electricity fairly well. Turns out that even if you touch the ceiling like that, you wouldn't feel a thing. And I learned that when I went to the Boston Museum of Science. And you know how we had that little Van de Graaff generator here that, threw off like tiny little sparks? Yes, Paulie was addicted to, remember that? Yes? Okay? Okay. Well, up at the Boston Museum of Science, they have a Van de Graaff generator that's probably like 40, 50 feet tall. It's humongous. It was actually there before the museum was there. It was part of MIT. They did research with it. When they no longer needed it for research, the city of Boston decided to make a museum around it, and thus the Boston Museum of Science was created. This huge Van de Graaff generator throws off humongous lightning bolts. So basically, it's like this. You got that rubber belt spinning round and round. Metal comb over here, connected to the ground. Electrons constantly being scuffed off onto the rubber belt, carried up to the top over here. And then the electrons scuffed off by another metal comb. And the electrons go onto that globe. And more electrons keep getting scuffed off the rubber belt onto that globe. And then down here, there's like, you know, imagine a wire cage bird cage, yes? But this was like human size. There was like a human sized bird cage over here, you know, with wires, you know, going down like this. And inside this big wire cage, okay, basically you had the operator in there. He's about this tall. You know, that's the size of the Van de Graaff generator. That's how big it is, yes? You have the operator in there, and he's basically controlling the lightning bolts. And of course, so many extra electrons would build up here that they would actually repel and push each other to jump through the air, which normally acts like an insulator, and crash into that metal cage. And once again, the person was 100% safe because they were inside that metal cage. So that metal cage would have these electrons take the outermost surface down to the ground. Well, I'm watching this guy. The lightning bolts, see that they are crashing. They are crashing onto that bird cage thing. Yes? And then the guy goes, while this is happening, crash. I'm talking your heart stops, like loud lightning bolts. Like, crash, crash, crash. What does he do? He goes, while this is happening, puts his hands on the inside of the cage. Yes? And takes his hands all the way, touching the inside of a metal cage. Metal nonetheless, yes? Metal's a conductor. He's touching the inside of this metal cage while the cage is being zapped. At the time, I was dog training, puppy training, my new Wheaten Terrier. Beautiful little puppy. And you have to keep it in a stainless steel cage. And I'm like, if he's safe in that metal stainless steel bird cage, the puppy should be safe. Yes? Okay? But of course, I would never try it out on my puppy. So what I do, I asked for a student volunteer. And I brought the cage in, and the student got in, and that's exactly what we're going to do after the break. So we didn't put a human in a bird cage like this, but we did put Paulie in a dog cage, and he survived the Van de Graaff generator, and then he survived the Tesla coil. So this whole process of being safe inside a metal box is called electric shielding. A way to protect yourself from electric fields is to put yourself inside a metal box. And not only does it work with extra electrons, it also works with a lack of electrons. So even if you have a metal conductor that has an overall positive charge, if it has an overall positive charge, the remaining electrons will spread out in such a way that even though the overall object is positive, inside the metal, the electric field strength is 0 everywhere throughout. So, this is a positively charged metal sphere. So, just in summary, extra electrons or lack of electrons do not spread out like gas inside of a container. They would not be like this. No. Okay? They end up taking the outermost surface because electrons repel each other, and they spread out in such a way that the electric field everywhere inside the metal conductor is 0. And this is called electric shielding.